This is an equation that you can use for the velocity function of an amplitude, and so the velocity maximum would be equal to 2 pi the amplitude times frequency, and you can find that the frequency is how many cycles the mass goes back and forth per second. Another way you can find that too is if the amplitude, the k value, the mass, you can figure out this as well. And so here's a sample problem using that. If we have a mass that's oscillates with an amplitude of 12 centimeters, you got a frequency of 3 hertz. Go ahead and try this one. You're going to get the total amount of energy of this system. And so go ahead and pause, and then when you're ready to check, you can hit play to continue. All right, so Vmax equals 2 pi AF, and the maximum velocity would be 2.6 meters per second. Therefore, the energy in the middle would be 1/2 mv squared. For the kinetic energy, should give 5.116 joules. And then let's go ahead and find the K value of the spring. So you can go ahead and pause the clip and try that. And when you're ready, you can hit play to continue to check that. All right, so that should be 709.39 newtons per meter would be the strength of the spring. All right, so in this one, what is the amplitude of the mass spring system? The velocity equilibrium is 0.78 meters per second. The frequency is 3 hertz. So in this one, it's going back and forth. I'm going to have you try this one as well. So go ahead and pause the clip and figure this one out. And when you're ready to check, you can hit play to continue. All right, so the frequency is 3 hertz. We know the maximum velocity. So the amplitude would be 0.0414 meters. So in terms of the derivation of what's going on with this, to find the maximum velocity, you have the square root of 1 over x squared over a squared, and we've looked at that. And remember, if something is sinusoidal in nature, we're dealing with an object that's going, that's approximating, moving in a circle, and that's where we get the values with the amplitude and the x values. And so as we take a look at this, a couple of things that are going to be helpful for us. We know the period is equal to 2 pi square root m over k, so that's going to be helpful for us. And therefore, with frequency, we know frequency is 1 over the period, so we can also get the frequency from 1 over 2 pi square root of k over m. So let's go ahead and try this one. This is a 300 gram mass and simple harmonic motion with 25 hertz frequency. And you want to find the force constant of the spring. So go ahead and pause the clip. Go ahead and give this a try. Then when you're ready to check, you can hit play to continue. All right, so the mass is 0.3 kilograms. The frequency is 25 hertz. And we should get 0.04 seconds for the period. Therefore, a K value of 7402.2 newtons per meter. Let's try this one as well. So we have the period, we wanted the period of a 200 gram mass attached to an ideal spring. The force constant is 1,000 newtons per meter. So go ahead and give this a shot. And when you're ready to check, you can hit play to continue. All right. So for this one, you should get 0.0889 seconds. All right, for this one, we have a bicycle with a rider that hit a bump and causes the 2 bike springs to compress. If the period of each oscillation is 0.75 seconds, we want to find the K value for each spring. So yeah, go ahead and pause the clip, give this one a try, and when you're ready to check, you can hit play to continue. All right, so 2 bike springs, each of them we'll assume is taking half the mass. So half of the mass, we could figure out the K 7018.39 newtons per meter would be the K value. So when we're graphing with the spring, it's going to be very, very important. This is some practice that we did, to be able to, make this from scratch. In other words, here, if we start the amplitude, compressed way up here at 120, over time it's going to be moving. So therefore, the velocity starts at 0 because, the amplitude, it's up at full amplitude, not moving, right? And then when it's released, it's falling, and so once it goes down and it's at equilibrium, it's going to have a negative velocity. Therefore, you have the maximum negative velocity down here. And then when it comes back into equilibrium at the 0 position, right, let's see, it's going down, and then the position, yeah, 0 here, and then down here where it's all the way, well, 0 position maximum, right? But when it goes all the way down to the bottom position, right, and it's all the way down there, velocity again is 0, and then, you know, it comes back up, and then as it's passing through the middle and it's going back up, there, you know, the position is 0, but you have a maximum positive velocity, and so on. Acceleration will be important with this as well to be able to visualize that. All right, so when you're and we'll do this in the lab as well. So again, just it's just going to take practice. That's